I think it's visible, right?
Yes, yes,
Yes.
yes.
Okay, nice. So, so this is a work done with my advisor Diptiman Sen, and I'll basically talk about some of the results of this paper. But I heard that hopefully there will be some undergraduate students who would be in the audience. So I have kept my talk as simple as possible, and I will also introduce um, a bit of second quantization language, which is used to describe, which is used in any condensed matter theory problems. So for the first few slides, I will really go over the basics of second quantization so that our younger fellows can understand the Hamiltonians and stuffs. Um, I'm sure the content is not that difficult, but it might be helpful for them if they just get an overview of second quantization. So let me start. So second quantization is the standard formalism, which is used to describe condensed matter problems. And we have particles, which are thought of as excitations on vacuum state, which is denoted by this ket 0. Um, and then we have creation and annihilation operators, which can produce or destruct particles by acting on Fock states. What are Fock states? I will come just next. And these operators always come with an underlying single particle basis, means position or momentum. So, and Fock states are denoted as a ket with which specify the number of particles with each of the quantum numbers in that single particle basis. So for example, if I this state nx1 equals to 1, nx2 equals to 2, this means that we are in a state where there is one particle in the position x1 and two particles in the position x2. Okay, and since the operators come with, so these C's and C daggers are those creation and annihilation operators. And since they come with a particular one particle basis, which is written as a subscript to the operator, but you can have another single particle basis, which can be written in subscript Q, then they can be interchanged via this linear transform, where this mu are the single particle states and in one basis, and Q is the single particle state for the other basis. So this is how you can do linear transformation between two bases. And uh, depending on the nature of the particles, um, the creation and annihilation operators follow some commutation relation, uh, which I have written down here. So C with C dagger, commutation or anti-commutation gives delta, uh, and for bosons, it's a commutation. For fermions, it's anti-commutation. Whereas for both creation or for both annihilation operators, uh, commutation relations give 0, or anti-commutation relation gives 0 for fermions. Okay, so now let me describe some of the how to represent some states in second quantization picture. So if I say C dagger K acting on 0, this means we are in a one particle state with one particle with momentum K. If I say C dagger Xj, C dagger Xi acting on 0, then we are in a state with, it's a two particle state with one particle at Xi position, another particle in position Xj. And 0 is the vacuum, as I said. And so annihilation operator acting on 0 for any quantum number Q gives 0. So, and one interesting thing about this second quantization language is states, if I specify like this, nq1, nq2, the number of particles in each state, they're already symmetrized and anti-symmetrized because they are constructed by these creation and annihilation operators, which follow this commutation relation algebra. So the states that we have specified already are symmetrized or anti-symmetrized. So here is one comparison of first quantization and second quantization. So in first quantization, we specify uh, some particle is in which state, and in second quantization, we just don't look at the particles individually, but look at the numbers and how many particles are in every single particle state. So here is the correspondence between states. So like if you have nq1 equals to 1, nq2 equals to 1, then this means for bosons, you have to symmetrize the wave function. Like first particles is in q1, the second particle is in q2, and then plus first particle in q2, second particle in q1. And for fermions, you have to anti-symmetrize it, and then you will have a minus sign. Okay. Now, so in my problem, I will be talking about some operators which will be written in this second quantization language. So I really want our audience to get used to what I'm talking about. So I'm using a general quantum number notation Q. So if I say C dagger Q, CQ, this means if it is acting on some state, then this will give the number of particles with that particular quantum number. Then I might be using operators like C dagger Q2, CQ1. What it means is it makes a particle hop from quantum number Q1 to Q2. So it's better to visualize it in terms of lattice sites. So if I give C dagger I, Cj, then it means a particle is hopping from jth site to ith site. And then I will introduce interaction in some later slides. And interaction, and in specifically density interaction I will be talking about. So these are denoted like two number operators product, that is like four creation or annihilation operators. So for this nq1, nq2 it generates interaction between particles at quantum numbers q1 and q2. So for example, if q1 and q2 equals to ith lattice site, then ni denotes the on-site interaction in the system. Okay, so that's all I wanted to say about second quantization. Now, so my talk is basically on how you can periodically drive a quantum system and produce states which are localized at the edge of the one-dimensional system. So before that, let me give you some motivation about a classical example. So periodically driven systems exhibit very unusual properties. So here's an example, a classical example, a rigid pendulum whose pivot point is periodically driven in vertical direction. So this pendulum is named after Peter Kapitza. So it's called Kapitza pendulum. And it can be shown that for very fast driving, we have an effective potential which looks like this. Then this oscillating pendulum will have stable positions at 0L and 0 minus L. Remember, 0L is the stable position for ordinary pendulum, but there is also 0 minus L. Means it can it is a stable position even if the bob is above the suspension point. So this is one fantastic thing that we can generate by periodically drive the system or some part of the system. So this will be my motivation or a classical motivation, but we are talking about quantum problems. So periodically driven quantum systems are generally discussed within the framework of Floquet theory. So that explains the title of my talk, Floquet. So Floquet theory basically deals with periodic Hamiltonians, which is like HT is same as HT plus period capital T. But since HT is time dependent, we cannot talk about energy eigenstates or eigenvalues because energy is not a good quantum number. And so what we do instead is construct an operator ut, which is like the evolution operator, but for a single period. So this is the notation to construct the time ordered product of the evolution operator. So time ordered product is, this symbol is used because um, you are actually constructing the operator from former time to later time, from right to left. And Hamiltonian at different times may not commute with each other. So that's why this time ordering symbol comes. And so this basically does nothing but takes a state and evolves it to a period of, to a time evolution of capital T. Now what we do is look for eigenstates of ut with some particular properties. So for our problem, we were looking for edge states. So that means that we look for states where ut psi 0 is equals to e to the power minus I epsilon t psi 0. So since ut is a unitary operator, the eigenvalues will be of the form e to the power I theta or something, but I write it like this. Then it is easy to read this epsilon as some analogous to energy. So e to the power minus I epsilon t is called the Floquet eigenvalue, and this epsilon is called quasi energy because energy is not a good quantum number. So this is like energy. So this is called quasi energy. And another thing is this epsilon is defined only modulo omega, which is equals to 2 pi by t. So if you shift epsilon by epsilon plus some p times omega, p is an integer, then you get the same number. So this quasi energy is defined only modulo omega. So I can compare it with like space periodic systems, which are defined, which are discussed in block theory. There you have moment, there you have crystal momentum, which is defined only over the Brillouin zone. So here is the Brillouin zone is over energy in, that's like omega. Okay, so let me come to our problem of study. So first we consider a model whose Hamiltonian is given like this. This is called 1D tight binding model on a finite size lattice of L sides. Hi, is there a question? Okay, fine. So what it says is, so this can be, so this is a non-interacting system. So this can be either bosons or fermions. It doesn't matter because there are no interactions. But what it says is a particle can hop from I plus 1th site to ith site or vice versa, and with an energy cost of minus g. So this is the tight binding model. Now, what I can say is, so by hopping, particles can reduce energy by minus g, which means now what kind of wave function makes this happen? Like, I'm just trying to guess what kind of wave function are the eigenstates of these Hamiltonian. So I think, okay, can anybody answer that? Okay, I think I should say this. Okay, so plane waves are the eigenstates of these Hamiltonian, where the particle is delocalized, and that's how you minimize the energy, and that's an eigenstate of this Hamiltonian. So my point is, if you have this kind of Hamiltonian, all its eigenstates are delocalized over whole lattice sites, and these are plane waves, but on lattice these are called block waves. Okay, now we drive this Hamiltonian with an electric field which is of this form. So it's a 1D model, so the electric field is only along x-axis. And this driving of electric field can be put in the system either as a on-site potential, which I have not done, or by a gauge transformation, I can put it in the phase of the hopping. So this was suggested by this gentleman fields. And this comes along like if you have an electric field, you can either write it as a gradient of a scalar potential or a time derivative of a vector potential. So it depends on which gauge you choose. So if you choose only that there is only a scalar potential, you can write it as an on-site potential. Or if you choose the magnetic vector potential and that's derivative, then this electric field can be incorporated as a phase in the hopping. So from this Hamiltonian H naught, if I drive the system, I get to this Hamiltonian, which is actually driven with electric field E equals to E naught cos omega t. And I have defined a driving parameter, which is like the amplitude of driving, as minus q over h bar times E naught times the lattice distance. So this is the driven Hamiltonian, and we have studied two systems. So this is the driven part, and we have studied two systems with this same driven part. One with a staggered on-site potential. You see the potential energy is V if the lattice site is even, and potential energy is minus V if the lattice site is odd. So this is a staggered potential. So that's a non-interacting system we have studied. And we have also studied a bosonic interacting system, which has this U by 2 times Ni type of interaction that I just talked about a couple of slides before. But the driven part is same. Okay, so let me go to the driven non-interacting system. So let's start with this staggered potential equal to 0. So we don't have a staggered potential. So the driven tight binding model looks like this, and we want to look for edge states of the driven system. And remember, I told you that we have to construct the Floquet time evolution operator and look for its eigenvalues and eigenstates, and which will say whether we have states which are localized at edge or not. So we construct the Floquet operator like this. So you divide the whole time interval. So I have done it numerically. So you divide the whole time interval 0 to capital T into n slices, and so T1 is the former time, Tn is the later time, and you have, so the time ordering symbol basically means this. So each slice is of delta t. So ut is basically e to the power minus I delta t h former time, then multiply in the left, and at the extreme left you have the latest time Tn. So this is the Floquet operator. Now we look for eigenstates of this Floquet operator, and for various values of parameters of the Hamiltonians like a or g or omega, and check whether if we can find states localized at the edge. Okay, now I'll just discuss something different because we are interested in finding states which are localized over edge. There is a quantity which is called inverse participation ratio, which I think I should say it now. So that so this quantity gives a large value if you have a state which is localized, and gives a small value if you don't have a localized state. So the IPR is defined like this. So if you have a wave function which is normalized like psi jm, jth is one of the eigenvectors, then IPR is defined as sum over all sites m mod psi to the power 4. Then if this psi j is extended like more or less equally over all sites, then IPR goes as 1 by system size. And if psi j is localized over a distance z, then this ij is of the order 1 by z. And this remains finite if I make the system very large. So if L is sufficiently large, if I plot all the eigenstate number with the corresponding IPR, then a high IPR will be a localized state and a low IPR will be an extended state. So as the name suggests, so it's inverse participation ratio. If the participation of many sites are there, then the inverse is less, so IPR is less. But if a state has only participation of very small number of sites, then inverse participation is large and IPR is large. So IPR only tells if a state is localized or extended, but then if you have the number, which number is high IPR, and plot the probability and check if it is localized at the edge or not. Okay, now we come to results. So we had this driven tight binding system without any staggered potential, and here I have chosen this hopping parameter G equals to 1, omega, the frequency of driving, equals to 1, and L equals to 100. And the driving amplitude is basically that A that I defined here, this A, this is the driving amplitude. This I varied over a distance, over a value from 0 to 30. And what I see is, although the static tight binding model has only states which are plane waves or block waves, this driven tight binding model admits eigenstates which are localized at some region. So for these regions of values of A, like here I'm pointing out, there are high IPR states in the system. And interestingly, what we see is the IPR peaks occur when the A by omega value is close to a 0 of the Bessel function. So to summarize, I have studied A from 0 to 30, and there are regions where you find high IPR states. I have plotted the 2 of the largest IPRs, and these high IPR states corresponds to states localized at the edge. So now a closer look of this maximum IPR plot allows us to classify the states which gives high IPR into 2 types. So there is type 1 where there are 2 high IPRs. So there both red and blue curves have high values, and here we have 4 edge states, 2 at each end of the system, and the regions of A are, I have mentioned it here, and what we see is the eigenvalues of those states. So eigenvalues are of the form e to the power I theta, and they are well separated from the eigenvalues of the bulk states, like the states which are extended over the whole region. And then there are type 2 region where there is only 1 state at each end, so 2 states, 2 edge states, and these are the regions of A where I find it, and the Floquet eigenvalues, they are equal to 1 and not separated from the bulk state eigenvalues. Okay, so here are the pictures. So type 1 edge states, there are 4 edge states. Here I have plotted 4 edge states, and correspondingly the eigenvalue plot looks like this. So these red band gives the eigenvalues for the bulk states which are extended, and the 2 dots here, which both are doubly degenerate, gives the 4 edge states that I just plotted here. So these are type 1 states. And then I have plotted type 2 states. So I have chosen a particular value of A, 8.44, where these type 2 states occur. So here we have 2 edge states, 1 at each end, and these black dots are the eigenvalues for those edge states. See, they lie inside the bulk of the eigenvalues of the bulk states. So what we found again was these edge states, what I said type 2 edge states, are not really edge states, although they have very high probability at the edge. They are actually made up of a superposition of many bulk states. That's why they are not, I mean, these eigenvalues are not well separated from the eigenvalues of the bulk states. Okay, now I can turn on this staggered potential. And again, I have this Hamiltonian, and we look for states localized at the edge. And similarly, we have to construct the Floquet time evolution operator and calculate the maximum IPR versus the driving amplitude A. And this I have done for different values of V. So I fixed the parameters G equals to 1, omega equals to 1. L I have taken 100 previously, but here I will take 100 and 101 because there is a difference that I will explain, and vary the driving amplitude from 0 to 30. And V and all of them I have done for V equals to +1 and -1. So here are the results. So this is the maximum IPR plot versus driving frequency for L equals to 100. And this is V equals to +1 and V equals to -1. What you can see is that there are a lot more regions in this parameter space where you have high IPRs, which means where you have edge states present, compared to this plot where the V was 0. And next, for L equals to 101, this is the plot that I have. So there are two edge states for red and blue curves. But one interesting thing to notice is that for L equals to 100, plus V and minus V plots are little different, whereas for L equal to 101, plus V and minus V plots are similar. So the conclusions from the plots are that if you have a staggered potential, then it can enhance the range of driving amplitude when we can find edge states, as I said. And then what we have also is IPR plots are invariant under V going to minus V transformation if L equals to odd in general, because what we found is there is a parity symmetry and a V going to minus V symmetry in the system if number of sites is odd. But for L equals to even, we don't have this symmetry. So that's why the IPR plots look different if if L is odd or L is even. Okay, so all this was done numerically, but we also tried to find if there is any way we can explain the presence of edge states by driving using some analytical calculation. So for that, we have to do is like this. So we start with the Hamiltonian H naught, V as our original Hamiltonian. This staggered potential part of the Hamiltonian is our original Hamiltonian. And then the driven part of the Hamiltonian is acted as a perturbation. So this is basically time dependent perturbation theory, but since it's driven periodically in time, and we are looking at states which are like the steady states in this periodic drive, this is a bit different from time dependent perturbation theory, and this is called Floquet perturbation theory. So if G is much less than the V, then this Vt acts as a perturbation to H naught, and we can have an effective Hamiltonian which is not time dependent up to a desired order of G using this Floquet perturbation theory. Now what we saw is even if G by V is of the order of 1/10, if we go up to order G square, then the effective Hamiltonian results agree very well with the driven system results. So the parameters I have chosen G equals to 1, omega equals to 1, L equals to 100, and V is 10.1, and A I have chosen to be 2.6. A is 2.6, meaning we are in the region where we have type 1 edge state, and also there is V. So these are the comparison between the edge states found in the driven system, like numerically that I have found, and from diagonalizing the effective Hamiltonian, we also find edge states similarly. So what I see is that for G by V of the order of 1/10, we can explain the formation of edge states by calculating this effective Hamiltonian in orders of G squared. Okay, so that's all I would like to talk about the non-interacting system. Let me go over to the interacting system. Here, the system is a Bose-Hubbard model. Here is the driven part, and here is the Bose-Hubbard interaction. So if there are, and I did the calculation with 2 bosons present in the system, not many bosons. So if in any side there are 2 bosons, then this operator gives value 1, and that's multiplied by, sorry, this operator gives value 2, and that's multiplied by energy cost of U by 2. So if there are two bosons present in a site, that has an energy U, whereas if there are not, if the two bosons are not on same site, then you don't have any energy. So you can be positive or negative, which will make it repulsive or attractive. And similarly, we have to find states for the Floquet operator, which are localized at the edge. And in this case, we were interested in finding two-body bound states which were localized at the edge. So since there are two bosons, the number of two-body basis states will be L into L plus 1 by 2. And I denote the basis as N1 comma N2, where N1, N2 denotes the position of the two bosons. So this is not a Fock state. This is another notation we have used. So N1 and N2 denotes the position of two bosons, but since they're indistinguishable, I have kept N1 less than equal to N2. So in this basis, I have constructed the matrix and then the Floquet operator and found if we can get any edge state from the Floquet operator. So the results are like this. So I have the parameters chosen G equals to 1, omega equals to 1. And for Bose-Hubbard model, since there are two particles, I couldn't go much beyond than L equals to 30. And I have chosen two values of A, the driving amplitude. A equals to 2.6 is where without interaction we had type 1 edge states, and A equals to 4 is where we had no edge state. Now here we have plot the interaction strength versus, so we have this Floquet operator, then we find the eigenstates and look for those eigenstates where the probability at edge is higher, and then plot those maximum probability at edge versus the interaction strength. So this is the result for A equals to 2.6, and this is the result for A equals to 4. So for A equals to 2.6, even without an interaction, we have a high probability at edge, which is just the result that I showed previously, that A equals to 2.6, we have type 1 edge states. So in zero interaction strength meaning we have a non-interacting system. But as we go, as we increase the interaction strength both in positive or negative direction, first the edge state probability, the probability at edge decreases, and then it goes little high, and then it keeps on increasing. Whereas for A equals to 4, without any interaction, we don't have any edge state. So because there are no edge states for A equals to 4. And then as we increase the interaction strength, it first goes high, then again drops, and then keeps on going high steadily. So what we can say is the presence of interaction modifies the existence of edge states. So overall trend is as you increase mod U, you get more edge state probability. That is, you get more probable that it is more probable that you will have edge states in the system. But there are some subtle things that it might go down at some moderate range of interaction. Okay, so this was again done numerically, but also we can do some Floquet perturbation expansion like the non-interacting case. And here the Hamiltonian to start with is the interacting part, U by 2 times ni minus 1 with a large U, and the time dependent perturbation is Vt, the driven part. And if G is much less than U, we can develop a Floquet perturbation expansion in G. And what we found is for G by U of the order of 100, even an effective Hamiltonian of order G can explain the formation of two-body edge states. So here I have the comparison. So G is 0.1 and U is 20.2. So it's like 200 times more. Omega equals to 1, system size is 30, and A equals to 2.6 is where without interaction I have type 1 edge states. And this is the probability versus n1 n2 plot. Just remember that n1 is always less than equal to n2. So this is the bound state, this is the edge state 1 found from the original driven system, and this is the bound state 1 found from the perturbative Hamiltonian that I calculated using this Floquet perturbation method. And similarly, there is for the state 2 also, this is the plots. So what we can say is even the effective Hamiltonian up to order G can explain that there will be bound states at edge if we drive the system and you have interactions present. Okay, so now I would go to how you can detect the edge states in a driven system. So this is done by transport calculation, and since the system is driven, I have to use a theory called Flowcase scattering theory. So what I did is I have done the transport calculation for the non-interacting system only because that's a little easier. So the Flowcase scattering theory goes like this. So I have a 1D wire which is connected to leads. The 1D wire has Hamiltonian with hoppings G, and the leads have hopping GL, and they are connected by this contact hopping GC. And the signature of edge states can be obtained by measuring the differential conductance across the two ends of the system. So the idea is if this left lead and right lead have an infinitesimal bias voltage between them, but that bias voltage is equal to the quasi energy of the edge state, then the differential conductance will have a peak at that energy. Okay. So let's suppose an electron is incident from the left lead with an energy E naught, which is connected to the momentum like this, the dispersion relation, and with a plane wave function psi n equals to e to the I k naught n minus E naught t, and the wire is driven with frequency omega. Then this electron, after reaching inside the wire, can gain or lose energy. So it can have, if it comes with an energy E0, it can have energy EP equals to E naught minus P omega t. So P can be positive or negative. So this is just a convention that I have put minus sign. Now that electron will get transmitted or reflected back to the leads, either left or right lead, but that will only be a propagating wave if this EP is an allowed energy in these leads. So EP is related to the momentum Kp according to this dispersion, but only if this EP lies between the allowed energy values of this lead, which is minus 2gl to plus 2gl, then Kp is real, and the transmitted or reflected wave is a propagating wave. So this is the electron coming in, this is the system, and so P are Floquet harmonics. It can gain energy in integer multiples of omega. So for each of these Floquet harmonics, I have a corresponding transmission coefficient, and similarly a reflection coefficient Rp. So it can go with any energy with the corresponding transmission coefficient, or it can get reflected back with any energy with corresponding reflection coefficient. And Rp, Tps are pth Floquet harmonics. Then the zero temperature, zero bias meaning the left and right lead has very infinitesimally small bias between each other, but that bias is equal to the incident energy of the electron. So the differential conductance is defined as G equals to di dv, and from Moskalett's and Butiker's result which is in this paper, this is the formula for the differential conductance. So E square is the electron charge, H is Planck's constant, and Vp is the velocity, which is dep dkp for the pth Floquet harmonic, and this mod Tp squared is calculated at the incident energy E naught. Now this differential conductance is calculated as a function of various differential various incident energies E naught, and a plot of G versus E naught will have peaks whenever the incident energy of the electron is equal to the quasi energy of the edge state, or it differs by an integer multiple of omega of the edge state energy. And remember that the system also have states which are extended or bulk states, but they might also make participation in conductions, but that can be suppressed if we make the contact hopping GC much less than GL. So this GC is the contact hopping. If I make it much lesser than GL or G, then the bulk state contributions are suppressed. And there is another point I should mention, is that for these edge states to transmit the electron, what should happen is that edge states from two sides of the system should hybridize, which means they should have same energy, and this hybridization will allow them to form a channel between the two ends of the system, and through that the electron can pass through the wire. So this I will this I will talk about more in some next slide. But here is the differential conductance versus incident energy plot. I have chosen GL equals to 1. GC is much smaller because I have to suppress the bulk state contribution. It's 0.01. And L I have chosen 10 because the system size should be small for that edge states to hybridize. And omega I have chosen pi by 4 because I wanted it to be different from G. Otherwise, there are some funny things that happens in the plots. And A by omega I have chosen 2.5. That is where we have type 1 edge state in the non-interacting system. So this is the plot for Floquet eigenvalues of edge states. These are the bulk state eigenvalues, and these separated dots are the edge state eigenvalues, and they appear, so they have values minus 0.59 plus minus 0.8 I, and that corresponds to the quasi energy of plus minus 0.2756, but this is defined modulo omega, and exactly where those are the places where G has peaks if E naught equals to this quasi energy or plus minus P omega. So this is the plot for G versus E naught. So these are the peaks which I am talking about, and they correspond to the energy this plus minus P omega. Okay, so now I was talking about system size has to be small. Is that because the edge states from two ends need to hybridize? But if the system size is larger, then since the edge states have very exponential fall off in the bulk of the system, if the system size goes beyond a certain length, the hybridization can be exponentially suppressed, and that is when the differential conductance is dropped, as you can see, beyond L equals to 20. Okay, so that was all. So let me summarize. So tight binding model in one dimension can host one or more edge states if it is driven periodically in time. Remember, without periodic driving, we all had is extended states. And then the range of driving parameters, like the amplitude of driving, where such states, edge states occur, can be enhanced if we have staggered potential present or an on-site Bose-Hubbard interaction. And the edge states in these non-interacting systems can be detected by calculating the differential conductance across the different wire, which is an experimental thing. Experimentalists can measure differential conductance by attaching metallic leads to the system. But one main problem of this thing is to control the driving amplitude and many other things. It's very hard to implement these things in real materials, but in optical lattice, if it is shaken periodically, and we have ultra cold atoms trapped in optical lattice, then all these results can be really tested, because in ultra cold atoms you can actually control all these parameters better than in real materials. So all I talked about is how you can form localization at edge by periodic driving. So here is one example of experimental realization of a periodically driven system in a Shaken optical lattice. So this was done by Linear et al, and this appeared in Fitzgerald letters in 2007. So what they did was they had a Bose-Einstein condensate of 5 into 10 to the power 4 rubidium atoms, and they kept it on an optical lattice. And so BEC is like everything is localized at a particular momentum k equals to 0, and then it was made free to expand by tunneling. So the tunneling can be actually understood numerically, mathematically by the hopping that I was talking about. So it's just hopping. Now this lattice was shaken sinusoidally, and this mimics a periodically driven quantum system. Then what they found was the tunneling amplitude J effective by J followed this curve. So this is what I mean, one can find this dotted line is what we can find analytically, because J effective analytically is J times Bessel function of the K0. K0 is defined as the driving parameter. And experimentally also they found that the J effective follows this theoretical prediction. So it goes to 0 whenever it reaches, so that whenever K0 is a Bessel 0, and it is maximum when K0 is 0. So actually you can do these kinds of localization by periodically driving a quantum system. And that's all I wanted to say. Thank you.
Okay, so thank you, Samudra. That was a wonderful talk. I think now we can accept questions from the audience. So over to RC sir.
No, I was actually just clapping, but I also have questions. But if students have questions, then they should ask first.
Oh, I thought. Okay. So we have a question actually. Ashif Akram, can you please unmute?
Hi, it was a nice talk. My question is, in one of the graphs, you showed that as you increase this mod u, the interaction strength, the system has more probable edge states, right? There are two graphs, yeah. So in the second graph, when a is 4.0, there is a kind of noisy sinusoidal kind of structure.
Yeah, actually it's not sinusoidal, because if we increase the interaction strength more, then it just steadily goes high.
Okay, so in that region only, until, for example, let's say 7.5 or 10, it's a kind of sinusoidal structure. Now I'm wondering, around 3 or 4, it has some peaks, right? There are peaks in both sides.
Yes.
Basically, on an aggregate coarse grain level, what is actually giving rise to these peaks? Unlike, for example, A equal to 2.6.
Yeah, so actually this, I really don't have an answer to what's really happening. So this was done numerically, and so for, interestingly, they only have 8 states only for a very small region of U, and then there is a dip. For these moderate values of interaction strength, I mean, we found to have 8 states in the system.
This is not numerical fluke, for example. It's a solid.
Yeah, it's a solid. Yeah, I mean, so what we showed is, if we construct, we constructed the Floquet evolution operator over a time period, but from that, if we can construct the effective Hamiltonian just by hand, like I just called that effective Floquet operator equals to e to the power minus I h effective times t.